first we want to do chemistry practice. This passage I got from here. It will be the first link on the Google Drive. I'll also be showing on the screen, but this is the source. I'll give you guys maybe 5 to 6 minutes to read this. Shouldn't really take longer than that. It says originally this passage has 7 questions. If you open up the link, I'll tell you we're not going to be doing all of them. We'll do 4 or 5 for them that I thought were like the best. The others you can obviously, if you want to go on your own, feel free to, but I won't be going over them in this lecture unless you guys have questions about them. I just thought these 4 questions that I picked out were the most high yield, and they were the most like different from each other, and they're like more representative of chemistry as a whole. But take 5 minutes just to read through the passage and kind of familiarize yourself with it. You can always just go back to the passage, and I highly encourage when you're reading these questions, go back to the passage. Okay? So the correct answer is B, and I'll go over why. So the main reason that, and you can look if you're all signed in on the Jack lesson, they have their own explanations. I'll go based off the way that I thought about it. So we know that MO is complexed with lysine, right? This involves like knowing the different amino acids. So you have to know what is lysine. It's an amino acid, but more specifically, it's actually a basic amino acid, right? It's a positive one. It's one of the basic amino acids. So because of that, whenever it interacts with something, it acts as a base, right? If the lysine is acting as a base, you need an acid to counteract that. So the MO would be acting as a Lewis acid, right? And remember that Lewis definition, I said it's not super common in my acid-base lecture, but Lewis acid just means electron donor or acceptor. That's what the Lewis acid-base definition is, right? So in the normal sense, you wouldn't think of MO, especially as an atom, as an acid or base because it doesn't have an OH, doesn't have an H to donate, right? So it's just an atom. But in the Lewis sense, it can act as an acid or a base, and in this case, it does act as an acid because something else is acting as a base. Okay. And these two are not really related. So C and D are those are something different. So amphipathic and amphiprotic, I don't think you'll pretty much ever see anything where that's the right answer. So it's very, very rare that you have to know what that is. Okay, so I think this is actually question 3, not question 2. But I actually like this question a lot. So and remember, you guys can use periodic table, and if you're using the site, there's a periodic table button. Otherwise, you can just look it up on another tab or on your phone. The periodic table is, but yeah. So the correct answer is actually A. And this is actually a trick question, which actually did get me when I first saw it. So you may have thought, because MO is an atom, right? And that's what we were talking about in the first question, the MO atom, right? It's the element on the periodic table. This asks what is the electron configuration of the ion, the molybdenum ion, not the molybdenum atom or the element, right? So first thing you have to figure out is, well, what is the ion? Should have it written here. Okay, so if you go back to the passage, and this is why reading the passage is important, especially when you get caught up on these one-word difference, right? In the passage, and you can go back to find this, it says this is the combination. And in this specific combination, lysine is neutrally charged, right? Like I mentioned, lysine is usually positively charged. We know at base pH, it's positively charged. It's a basic amino acid, but here specifically said it's neutrally charged. So that means the 2 lysines are 0, but the overall charge is +2. So that +2 has to come from somewhere. They said it's not from the lysine. It has to come from the MO, right? That means the MO ion has to be 2+, because this overall thing is 2+. They said the lysine is neutral, so that means MO is 2+. So the MO ion has, because it's 2+, normally it does have 6 more electrons than krypton, right, or Kr, right? But in the case that it's 2 plus, it actually only has 4 more electrons, right? So you have to know that this exponent has to be the sum of the exponents has to be 4. 4 obviously works. This one is 1 plus 5, that's 6. That would work for the element, and this would actually be the correct answer for the element, but not for the ion. This is 4, so this works. And this one is 3, so this doesn't work in any case, right? So now you have to decide between A and C. Well, remember that the s orbital can sometimes get filled before the d orbital, like in the case of 3D and 4s, right? 4s sometimes gets filled before 3D. However, in this case, it's not as effective to do one. So this is the s orbital, and this is the d orbital, right? It's not as effective to do something like this rather than just doing something like this, where you just fill up the d orbital, right? Okay, so this is actually better. And remember, the d orbital can have 5 in a line, and then it starts to go down, right? So you can have 10 total. But in this case, it would be more effective to just fill up 4 d orbitals rather than have 1 s orbital. So that's why the answer would be A. Any questions about this at all? This one's a little bit tricky, and especially if you really didn't catch this one word that changed the whole question completely. So be careful for that. Okay. Okay. So please take a minute to think about this question. Okay. So the correct answer is actually C, and I'll go over why. So the first thing thought you may have is hydroxyl group, right? Because you see an OH, you know hydroxyl means OH. So you may say, well, this has an OH, so it must be A. Well, that's wrong, because hydroxyl actually means COH, right? So you have a carbon, doesn't matter which carbon, and then it has an OH attached to it. This has an OOH, right? So this is actually a peroxide, not a hydroxyl. So this would not be the correct answer. Next thing you may think of is ether, because you remember ether is like this, right? It's an O surrounded by 2 carbons. Again, this is not the case because it has a carbon here, but it has an OH here. So again, it's a peroxide. It's not an ether, right? It's not an ether because it's peroxides. This group is neither a hydroxyl or an ether. Okay. Next thing is this tert-butyl, right? And what is a tert-butyl? Well, it's 4 carbon, because you know butyl means 4 carbons, and tert means tertiary. So that means it's a carbon that is attached to 3 other carbons. So it's a carbon that's attached to 3 other carbons. How would you attach 3 other carbons? Well, like this. Okay. So, and then you can have one other R group, doesn't matter what group that is, but this has to be a carbon, this has to be a carbon, this has to be a carbon. You see this center carbon actually is a tert-butyl because it has carbon here, carbon here, carbon here, right? So it is a tert-butyl. This one carbon is a tert-butyl. One second, please. Sorry about that. And lastly, secondary butyl, again, same thing. Butyl means 4 carbons, so you know you have 4 carbons in a chain connected to each other, essentially. And sec means secondary, means kind of the opposite of what tertiary means. So it's attached to 2 carbons, right? So it'll be like this, and then it'll have some R group and some R group, right?
Yes, you could.
Sorry about that. So there's carbon here, right? Secondary, usually secondary you'll see is if you have something like this. And see over here, right? If it's just in a straight line, or actually it needs to draw it like this. Actually, forget this line, but it's if you do it on a straight line, this is a secondary because it also has 2 hydrogens but 2 carbons. This is a secondary, this is a secondary, this is a primary, right? These edge pieces are primary, whereas these middle pieces are secondary. In this case, this one's a tertiary because that's 3, okay? And this question is just simply about knowing the different groups. And remember, again, OH, yeah. Okay. Last question. This one's going to require a little bit more, I think, thinking and a little bit more like actually drawing out. And this is from the passage, but this is the step. If you're looking at the passage, it might be easier to see it. There's like a figure that just showed this. I just want to put it here as well for easy viewing. So the correct answer is actually A. I know if you just look at this diagram that I posted and just think about it this way, you won't really get the answer, but you really have to focus actually on these 2 things, right? So remember that this happens in 2 steps, not 1. No, it says step 2 here. It's actually 2. Step 2 is actually 2 steps, right? It's not just 1 step. And actually, I think the actual explanation on Jack Weston is really good. So I'm going to actually borrow their diagram, right, in which they show the 2 steps, okay? So immediately, step 1 of step 2 is to go from this to this, right? Right. So using compound 1, which is right here, shown here, right? You can actually turn this, which is what we started with, into this intermediate. And then the second step, you turn that intermediate into something else, right? And that's the product. Okay. So now let's look at this. Oxidation of the alkene and reduction of the alkene. Well, this alkene, the alkene's right here. It's a double bond, right? This alkene, in neither of the steps does it ever get even touched. So automatically, this is wrong because the alkene doesn't get oxidized or reduced, doesn't get touched at all. So those 2 are out. Now it's between A and B, right? Well, like I mentioned, the OOH is called a peroxide, right? So what happens to this peroxide as going from step 1 to step 2? If you just look here, it might look like reduction, right? If you just go like this, I'm sorry, it might look like oxidation, right? Because you're losing an H, right? But it's actually, it's hard to see in this. It's easier to see it if you do it in 2 steps. What happens to the peroxide? Well, it turns into OH. What it means is it actually lost an O. It donated an oxygen. Well, oxidation is getting oxygen onto yourself. So giving up oxygen is oxidating something else, right? Because you're giving up oxygen. So you're oxidizing something else. And if you oxidize something else, that means you yourself are getting reduced. That means this peroxide actually got reduced in the first step. And then go from OH to double bond O. I like to remember oil rig. Oxidation is loss, reduction is gain, right? And that refers to hydrogens to protons, right? So since it lost the hydrogen, you use oxidation as loss, so the alcohol got oxidized. There you go. Remember, oil. Usually for oxidation reduction reactions, oil rig and calculating the kind of like hydrogens is the easiest way, and that I've seen. The protons or the hydrogens, these ways track their movement, right? But in this case, the first step where you're going from peroxide to OH, you didn't really have any obvious movement of protons. There actually was movement, but it's not as easy to see because usually you track protons through hydrogens and hydrogens weren't exchanged. But remember, obviously, oxidizing, as the name implies, is giving up on oxygen to something else, right? And you know when like iron or something gets oxidized, it gains oxygen, right? Because it reacts with the oxygen. So reduction is just the opposite, just losing an oxygen, because oxidizing is gaining an oxygen, okay? But again, oil rig is generally, and tracking hydrogen is generally the easier way in most cases, but Any questions about this before we move on to the next passage? Or if either of you have looked at the other two questions that were in this group and that went along with this passage that I didn't show yet, you want to ask those, you can as well, and I'll go over them. If not, then look at them on your own time and try them.